Section 13.9, the implications. Okay, so we talked about kinetic molecular theory. What are the ramifications or implications of this? Well, this helps us to understand the meaning of temperature, which I kind of talked about already. The Kelvin temperature is directly proportional to the average kinetic energy of the gas particles. So the gas particles moving faster, that's higher temperature. And the Kelvin temperature is important because 0 Kelvin is absolute zero. At 0 Kelvin, particle movement ceases. So nothing is moving. And so it's proportional to Kelvin temperature. There is a relationship between pressure and temperature. We've studied the gas laws that show us what happens. This explains why that happens. Why does the pressure change when you change the temperature? Well, when you increase the temperature, what happens to the movement of the particles? They move faster, right? When they move faster, they're going to bump into the walls more often. The particles bumping into the walls is what causes the pressure. That's what causes the pressure. So if you have more collisions with the walls of the container, you have more pressure. In addition to them colliding more frequently, they're also going to collide faster. Because when the temperature rises, they move faster, and so when they run into the wall, they're hitting it harder. So you've got it hitting it harder and hitting it more often. It also explains the relationship between volume and temperature. So if we keep the pressure constant, then the volume must increase when the temperature increases. The particles are speeding up. Pressure is force per unit area. If we're increasing the force and we want the pressure to be the same, we have to increase the volume, the area over which they're hitting. So in order to keep the pressure constant, if you heat up a gas, the volume will expand. When would we use that?
Tanks and propane, like the size of the tank?
Well, most of the things that we deal with gases don't really have containers whose volume can change. But with balloons are probably the one thing that we understand in real life where the volume of a gas can change. If you heat up a balloon, the pressure is going to change a little bit, but it's not going to be significant, but the volume is going to expand because it's trying to keep the pressure fairly similar. So you increase the heat and the volume gets larger. If you decrease, you put the balloon in ice water and it'll shrink because the particles are not moving as fast anymore.
But if you the reason the pressure can go is because the volume does go up. But if you take a compressed air temperature and heat it, that's why it would explode because the pressure goes up beyond the container.
So the container can't expand.
Right. If you take a container like an aerosol can, that's why they say don't incinerate, don't put it in the fire. Because when you take a gas in a closed container like that cannot expand in volume and you heat it, the pressure goes up. The container can only handle so much pressure and eventually it will burst. And you don't want to heat a can of beans without opening it either. So there's a little bit of gas and that's enough to expand and blow up the can of beans. And they'll be hot by that point and burn you, and it's a disaster.
Did you try that?
People have done that.
Oh, I thought this was like something that happened.
No, we haven't done that. But no, I've heard about it.
So if the volume is increasing but the container can't expand with it, then you'll have the explosion.
Well, the volume can't increase if the container doesn't get bigger.
So that's where the pressure is created.
So the pressure is increasing.
Okay.
Pressure and volume are inversely related.
So pressure, volume, and temperature, it's very easy to understand constant N, constant amount of gas, because it's closed. We're not adding gas, we're not taking gas out. Pressure, volume, and temperature can all change at the same time. So if you have a container that is rigid, a fixed volume, then you're controlling the volume. You're not allowing the volume to change. So then if you increase the temperature, the pressure's going to go up. If you have a container like a balloon where the pressure and the volume can change, then they will. And when you heat a balloon, it will get larger, but the pressure also gets a little bit bigger too, because to stretch the latex farther requires more pressure. So let's do some concept checks. You're holding two balloons of the same volume. One contains helium, one contains hydrogen. Complete each of the following statements with different or the same. Be prepared to justify your answer. So here we have two balloons, same volume, we're told. And we look at the pictures and we're like, yeah, they look like they're the same size. Are the pressures of the gases in the two balloons the same or different?
Same.
The same. Why?
It's atmospheric pressure. So it's the same. In the balloons?
In the balloons.
Because it
Because
doesn't
they're both
matter,
the same.
the gas inside the balloon doesn't matter.
Well, the balloons are the same size, so their volumes are the same. We can assume that their temperatures are the same because they're next to each other in the same room. So why would the pressure be different? There's no reason for the pressure to be different, right?
Would it make a difference because one's higher, or is that because it's helium?
That's because it's helium. The fact that they're different gases doesn't matter. Because whether you have, a 100-pound person or a 150-pound person in Wyoming, it doesn't matter. There's so much space, it doesn't matter. Gas state, the size of the particle doesn't matter. It's the number of particles.
So it wouldn't matter that H2.
We'll go through all these and see. So the temperatures of the gases in the two balloons, that'd be the same or different? The same. They're right next to each other. The number of moles of gas in the particle, in the balloons.
Number of moles.
The volumes are the same. The pressure is the same. They're both the same kind of balloon. The temperature was the same. PV equals nRT, right? PV equals nRT. So we're talking about moles. So the number of moles depends on the temperature, the volume, and the pressure. If the temperature, the volume, and the pressure are the same, then the number of moles is the same. So the number of moles of gas are the same. How about the densities of the two balloons? What is density? Density equals mass divided by volume. Are the volumes the same? Yeah. Are the masses the same? Number of moles are the same. What does let's just say it was 1 mole. What does 1 mole of helium weigh? 4 grams. What does 1 mole of hydrogen weigh? 2 grams. So, are the densities the same? No, the densities are different. Okay, now do you have a question?
Well, because we were going over the fact that number of particles, and
Mm-hmm.
that would change the volume, right?
Number of particles would affect the volume and the pressure or the temperature.
Well, so it doesn't matter that there's like H2 and then just 1 helium?
No, because the H2, those 2 hydrogen atoms are bonded together and they're 1 particle.
Alright, got you.
So that's like, this is probably not at all politically correct. So it's like you have regular people or conjoined twins. Okay, conjoined twins, that used to be known as Siamese twins, okay, they're attached to each other. Birth defect. They can't get away from each other. They're one unit. So hydrogen gas, even though it's got two atoms in it, those are bonded together. It acts as one particle. So if you have, water vapor, H2O, there's three atoms, but it's only one particle. So that's a good point to consider.
How can their moles be equal with their masses not?
Because mole is number of particles, but the particles weigh different amounts. So you could have five molecules in one balloon and 5 molecules in the other balloon. And it's the number of molecules that affect the pressure, the volume, and the temperature. That's the mole. Mole is number of particles, but they don't weigh the same because different gases have different...
You could have the same number of particles, but then the masses will be different.
The masses will be different, yeah.
I
Yeah.
was trying to do the whole conversion factor and try to make it.
Yeah, and that's a really important concept to have clear in your head. Yeah, the masses are on the periodic table. But that mole unit it's important to get through your head that is a counting number. That's how many, not how much it weighs. Any other questions? Here's another question. So here we've got 2 balloons, and it says that the volume of the neon is equal to 2 times the volume of the argon. So which of the following best represents the mole ratio of neon to argon in those balloons? If the neon balloon is twice as big as the argon balloon, does that mean it has the same number of moles as argon? Or does it have more or less? The volume depends on N. If you double N, you double the volume, keeping the other things constant. So if the neon balloon is twice as big, it must have twice as many moles. So the ratio will be 2 to 1. Any questions?
So like what would a 2 to 1? I mean,
1 to 2?
yeah, it would just be the factors.
Yeah. If it was 1 to 2, then the neon balloon, whoops. If it was the opposite, then the neon balloon would be smaller than the argon balloon. The fact that it's neon and argon doesn't matter. If you switched and made this balloon argon and that one neon, but you had twice as much argon as neon, then this balloon would be twice as big. So it's a very odd thing about gases. What the gas is doesn't matter for most of the things. All it matters for is mass.
What was your equation for density? Is T mass?
Mass over volume.
So like,
The densities will be different, but the number of moles will be the
I was
same.
kind of thinking back about the last one. So if you were, in the last one, if you were to add like more helium to the, it would be less and less dense.
That's a good question. So, to this one, if we add more helium to this balloon, how would that affect the density? Well, if you do not allow the volume to change, and you add helium, then it's going to become more dense because you've got more mass in the same volume. If you add helium and allow the balloon to expand, allow the volume to change but keep the pressure and the temperature the same, then the density will be the same. Let's think about hot air balloons. So let's pretend this is a hot air balloon. Okay, so here's a little basket like that. And then you've got this burner here. Hot air balloons are open at the bottom. And they actually have a little hole at the top too. And they have this burner in the basket or above the basket, depending on how safe you are, that heats the air. So you've got this open balloon. It's basically like a giant pillowcase or something, this big sack, open on the bottom, and you're heating the air. What does that do to the gas particles? Makes them move faster. So they're going to spread out more. They're going to open up that balloon. They're going to push against it. The pressure, though, can't increase because the balloon is open. So as you heat the gas particles are going to escape from the bottom and the little vents at the top. But they're going to keep expanding and expanding and expanding. And so you've got gas molecules leaving the balloon. What does that do to the mass of the air in the balloon? It goes down. You're causing this balloon to be full of a less dense gas. And that's what lifts the balloon up. Because when you heat a gas, it expands. The volume gets bigger, right? If the volume's larger, the density goes down. So when you heat a gas and you allow it to expand, then the density goes down. And so they can use this burner to control the density of the air in the balloon. If you want to come down, well, you turn down the burner and let the air cool down a little bit. You don't want to just shut it off because you don't want it to plummet to your death. That's not a good idea. If you want to go higher, you crank up the burner. You can't control where you're going, though. You're at the whim of the winds. The best you can do is to understand that the wind is maybe going in different directions or different speeds at different elevations. And so you go up there and it's blowing you this way, and then if you go down, it might be blowing you slower or something. So we did that one. Let's look at this one. Well, I thought I got rid of this question. I don't want to talk about this question. We're not going to talk about that question.